Welcome to WikiPodcast. How do spinning magnets power your home? Just, think about that for a second. You flick a switch and bam, lights your computer, everything just works. And almost all of that energy, it starts with something rotating near something magnetic. It sounds, well, almost like magic, doesn't it?
It really can feel that way sometimes.
Yeah.
But it's not magic, it's pure physics. Specifically, it's a principle called electromagnetic induction.
Right, electromagnetic induction.
It's this invisible engine that's really driving so much of our modern tech. You know, the huge generators powering cities, tiny little transformers inside your phone charger. It's this phenomenon where basically a voltage, or what physicists call an electromotive force, F gets produced across a wire, or any conductor really, when it's put in a changing magnetic field.
And that word changing, that's the absolute key here, isn't it?
Utterly central. Without change, nothing happens.
So this is part of our continuing exploration of physics, and today we're diving deep into electricity and magnetism, focusing right on this. Our mission, using the sources we've looked at, is to unpack electromagnetic induction. Where did it come from? What are the rules? How do we actually use it? And maybe what are the tricky bits?
Yeah, hopefully by the end you'll have a much better feel for what's going on behind the scenes when you turn on the light.
And what's amazing is how, well, new this discovery is, relatively speaking.
Oh, definitely. In the grand timeline of physics, it's quite recent. We're talking less than 200 years ago.
Yeah, it wasn't figured out by Newton or anything. It really came about in the 1830s.
That's right. The big name usually credited is Michael Faraday in England around 1831.
But the sources also highlight Joseph Henry in the U.S.
Yes, independently, he made essentially the same discovery right around 1832. It seems it was just an idea whose time had arrived.
So tell us about Faraday's experiments. They sound quite fundamental.
They were remarkably clever, especially given the equipment back then. One of the really famous ones used an iron ring, kind of like a donut shape. He wrapped two completely separate coils of wire around it on opposite sides. One coil he hooked up to a battery.
Okay, so that creates a magnetic field in the iron.
Exactly. And the iron guides that field around the ring so it passes through the second coil. He connected that second coil to a galvanometer, basically a sensitive current detector.
And what happened?
This is the crucial part. When he connected the battery to the first coil, the galvanometer needle on the second coil gave a little jump, a momentary current.
Just for a moment.
Just for a moment. Then, even with the battery still connected and current flowing steadily in the first coil, the needle went back to zero. Nothing in the second coil.
Huh, okay.
But then when he disconnected the battery from the first coil, the needle jumped again, but this time in the opposite direction.
Wow, so it wasn't the magnetic field just being there that caused the current.
Precisely not. It was the change. The change when the field appeared and the change when it disappeared. That wave of electricity, as he called it, only happened during those transitions.
That's the core insight right there.
Absolutely. And he saw it in other ways, too, like just pushing a bar magnet into a coil of wire or pulling it out again that also induced a brief current. The motion, the change, was key.
And the Faraday disc. That sounds important for generators.
Ah, yes, the Faraday disc. You could argue it was the very first electrical generator. He spun a simple copper disc, like a coin, between the poles of a horseshoe magnet. And as it spun, a steady DC current flowed from the center of the disc out to its edge, or vice versa. Continuous motion created continuous current as long as the motion and the field were there.
Okay, so he demonstrated the effect. But explaining why it happened was the next step.
Right. Faraday himself thought in terms of lines of force, these invisible magnetic field lines filling space. He imagined that cutting these lines or changing the number of lines passing through a circuit was what induced the current. It was very visual, very intuitive.
But maybe not quite mathematically precise yet.
Exactly. That piece of the puzzle came later, mainly with James Clerk Maxwell. He took Faraday's brilliant physical intuition and formalized it into a precise mathematical law, what we now call Faraday's law of induction.
Part of his grand unification of electricity and magnetism.
A huge part. And we also need to mention Heinrich Lenz. Around 1834, he figured out the rule for the direction of the induced current, Lenz's law.
Okay, so let's dig into those core principles, Faraday's law and Lenz's law. First up, magnetic flux. What exactly is that?
Right, magnetic flux. Think of it visually. Imagine magnetic field lines like you just mentioned. Flux, usually written as I with a little b, is basically a measure of how many of those magnetic field lines are passing perpendicularly through a specific area.
Like the area inside a loop of wire?
Exactly like that. So if the magnetic field is stronger, more lines pass through, higher flux. If the area of the loop is bigger, more lines pass through, higher flux. If you tilt the loop so the lines just skim past, the flux drops. It's about the effective amount of field going through the area.
Okay, so it's like the magnetic field flow through a surface. Got it. How does Faraday's law connect this to voltage?
Faraday's law states that the size, the magnitude of the induced voltage, the EMF, in any closed circuit is directly proportional to how fast the magnetic flux through that circuit is changing over time.
Not just if it changes, but the rate of change.
Yes, the rate is crucial. The faster the flux changes, the bigger the induced voltage.
So if I push a magnet into a coil really slowly, I get a little blip of voltage.
Right.
But if I jam it in there quickly, I get a much bigger voltage spike.
Exactly that. That's the dB part in the equation. E equals dB/dT, the rate of change of flux.
And that minus sign, that's Lenz's law you mentioned.
That's Lenz. The little negative sign packs a punch. It tells us the direction of the induced EMF, or current. Lenz's law basically says that the induced current will always flow in such a direction that the magnetic field it creates opposes the very change in flux that produced it in the first place.
It fights back against the change?
It fights back. It's nature's way of conserving energy. You try to increase the flux, the induced current makes a field trying to decrease it. You try to decrease the flux, the induced current makes a field trying to prop it back up.
So that's why it takes effort to push a magnet into a coil if it's connected to something. You're fighting that opposing magnetic field created by the induced current.
Precisely. That mechanical work you do, pushing against the opposition, that's what gets converted into electrical energy in the circuit. No free lunch.
Makes sense. Now, what if you want more voltage? Can you amplify this effect?
Oh, definitely. The easiest way is to use a coil with lots of turns of wire, instead of just one loop. If you have, say, N turns all wound together, and the same changing flux passes through each turn, the total induced voltage is essentially N times the voltage induced in a single turn.
So more turns equals more voltage.
Exactly. The equation becomes E equals N dB/dt. That N factor is why coils are so common in things like generators and transformers. It multiplies the effect.
Okay. So to induce this voltage, we need changing flux. How practically do we make the flux change?
Well, there are a few main ways the sources mention. You can change the strength of the magnetic field itself passing through a fixed loop. Think of an electromagnet where you vary the current.
Yeah, okay.
You could change the area of the loop that's sitting in the magnetic field, maybe squash or stretch a flexible loop.
Right.
Or, and this is a really important one, you can change the orientation of the loop relative to the magnetic field lines.
Ah, like spinning the loop.
Exactly. Imagine a constant magnetic field, like between the poles of a magnet. If you spin a coil of wire in that field, the angle between the coil's area and the field lines is constantly changing.
So the number of lines going through the loop changes continuously, even if the field strength and the loop area stay the same?
Precisely. Maximum flux when the loop face is perpendicular to the field, zero flux when it's parallel, and everything in between as it spins. That continuous change in flux induces a continuously changing voltage.
That sounds exactly like what happens in a generator. Back to the spinning magnets idea.
It is the core principle of most generators. And it's interesting, the physics works out the same whether you spin the coil in a fixed magnetic field or spin the magnet near a fixed coil. It's the relative motion, the relative change in orientation that counts.
And that relative motion idea was important for Einstein, too.
It was. Maxwell had already noted the symmetry, and Einstein considered this phenomenon the fact that inducing a current depends only on the relative motion between conductor and magnet as a key piece of evidence on his path towards the theory of special relativity. How the same physical effect looks slightly different depending on who's moving.
Amazing. From simple wires and magnets to the nature of space and time.
It shows how deep these fundamental principles run.
Okay, so we've got the history, the laws, the concept of flux. Let's talk applications. How does all this theory translate into the tech we use every day?
Right, this is where induction becomes really tangible. The number one application, without a doubt, is electrical generators.
This is how we actually make the electricity in power plants.
Absolutely. There are energy converters. They take mechanical energy from spinning turbines driven by steam, water, wind, whatever, and turn it into electrical energy using induction.
So how do they do it? Is it that spinning coil idea?
Pretty much. Most large generators involve either spinning large coils of wire within powerful magnetic fields or spinning powerful electromagnets inside stationary coils of wire. Either way, you get that crucial relative motion and changing orientation.
Which means continuously changing magnetic flux through the coils?
Exactly. And according to Faraday's law, that continuously changing flux induces a continuously changing voltage, an alternating current, or AC, in most power plants.
And linking back to Lenz's law, generating this isn't free, right? There's that opposition.
Yes, absolutely crucial point. Let's think about the Faraday disk again. When current is induced and flows through the disk, that current is moving in a magnetic field. This creates a magnetic force that opposes the rotation of the disk.
It tries to slow it down.
It does. So, to keep the generator spinning at a constant speed and producing electricity, the turbine has to constantly exert a force, do mechanical work, against this magnetic drag force.
And the mechanical energy the turbine puts in equals the electrical energy taken out, plus any losses like heat.
Precisely. It's energy conversion in action, perfectly illustrating Lenz's law. You have to push against the opposition created by the induction itself.
That makes so much sense. Okay, what's another big application? Transformers were mentioned.
Transformers. Absolutely essential for our power grid. They allow us to efficiently change the voltage and current levels of AC electricity.
We need high voltage for long-distance transmission to minimize losses, but low voltage for safety in our homes.
Exactly. And transformers do that using induction. A basic transformer has two separate coils, a primary and a secondary, usually wound on a shared iron core.
No direct electrical connection between them.
None at all. You feed an alternating current into the primary coil. Because the current is constantly changing, rising, falling, reversing it, creates a magnetic field in the iron core that is also constantly changing, constantly fluctuating.
A changing magnetic field means changing magnetic flux.
Right. And the iron core guides this changing flux through the secondary coil.
And that changing flux passing through the secondary coil induces a voltage in it, according to Faraday's law?
It's called transformer EMF. Since the flux change is driven by the AC in the primary, the induced voltage in the secondary is also AC, at the same frequency. By changing the ratio of turns between the primary N1 and secondary N2 coils, you change the voltage ratio. More turns on the secondary steps the voltage up, fewer turns steps it down.
It's really quite elegant, just changing flux, doing all the work.
It's what makes efficient long-distance power transmission feasible. The sources mentioned a couple of other interesting uses too, like current clamps.
Oh yeah, those tools electricians use. They clip around a wire.
That's the one. It's basically a portable transformer. The wire you clip it around acts like a single-turn primary. The clamp itself contains an iron core and a secondary coil. The changing magnetic field from the AC current in the wire induces a current in the clamp's coil, which the meter measures. Lets you measure current without breaking the circuit. Very clever.
Ingenious. And magnetic flow meters.
Yeah, another neat application, used for measuring the flow rate of conductive liquids. You set up a magnetic field across a pipe, and as the conductive liquid flows through it, the moving charges in the liquid experience a force, inducing a voltage across the pipe, perpendicular to both the flow and the field.
Like the charges are the conductor moving through the field?
Exactly.
Yeah.
And the faster the liquid flows, the bigger the induced voltage. The source even gives the formula E equals BA. You measure the voltage E, the field B in pipe, with ES, so you can calculate the velocity V.
Wow. So making power, changing voltage, measuring current, measuring flow, induction is really versatile.
It is incredibly fundamental. But, like many powerful things, it can also cause problems if you're not careful. Which brings us to eddy currents.
Right, the unwanted side effect.
Exactly. When you have a changing magnetic field penetrating not just a wire coil, but a solid chunk of conductive metal, like the iron core of a transformer or the metal parts of a motor, it doesn't just induce voltage along a specific path. It induces currents that swirl around within the bulk metal itself. These are eddy currents.
Like little whirlpools of current inside the metal.
That's a good way to think of it.
Yeah.
And because the metal has resistance, these swirling currents generate heat, I²R losses, just like current in a wire.
So they waste energy and make things hot.
Yes, they're a significant source of energy loss, often called core losses, in motors and transformers. They reduce efficiency and can contribute to overheating.
So how do engineers deal with them? You can't just turn off induction.
No, but you can make it much harder for the eddy currents to flow effectively. The main technique is called lamination.
Lamination, like laminating a document.
It's sort of the same principle of layers. Instead of using a solid block of iron for the core, engineers build it up from lots of very thin sheets or laminations stacked together. Crucially, each sheet is electrically insulated from its neighbors, often just by a thin coat of varnish or even an oxide layer like rust.
How does making it in thin, insulated slices help?
Think about those swirling eddy currents. In a solid block, they can form large loops and flow easily through the metal bulk. But in a laminated core, those potential large paths are broken up by the insulation between the sheets. The eddy currents are forced to stay within the confines of each thin lamination.
Making the loops much smaller and restricting their flow.
Exactly. By confining the currents to these much smaller paths within thin sheets, their magnitude is drastically reduced, and therefore the heat they generate, which goes as the square of the current, is massively reduced.
So that dramatically cuts down the energy waste.
Hugely. The source mentioned it can cut eddy current losses down to maybe 1% or so compared to a solid core. It's a vital design feature. A similar idea is used in windings carrying very high-frequency currents using bundles of individually insulated wires, Litz wire, instead of one solid conductor, again to fight eddy currents within the wire itself.
Fascinating. Both using induction and fighting its unwanted effects requires clever engineering.
It really underscores how engineers have learned to work with this fundamental physical principle.
Okay, so let's try to wrap this up. Electromagnetic induction discovered by Faraday and Henry, mathematically pinned down by Maxwell, directions sorted by Lenz. It's this fundamental link between changing magnetism and electricity.
It's the absolute bedrock of electrical generation, power transformation, and pops up in all sorts of measurement devices too. It really shows how deeply intertwined electricity and magnetism are.
And understanding it, especially Lenz's law, gives you that sense of conservation, that pushback against change that seems to be built into the physics of energy conversion. You don't get something for nothing.
That opposition is inherent in the process.
So thinking about all these applications, from huge generators to tiny sensors, what everyday device do you think might be using electromagnetic induction in a surprising way? Thanks for listening. Write us your opinion in the comments on what everyday device do you think might be using electromagnetic induction in a surprising way. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.